Greetings, fellow mathematicians. We're going to solve a second order ODE with non-constant coefficients and initial conditions with a power series approach. Now, before we get started with the problem, make sure you're comfortable with where we're starting. We begin with a power series representation for our function or solution, y, and then we have corresponding power series representations for y prime and y double prime. The link to the videos below, make sure you're comfortable where these come from. We go through it in detail. We basically use all three of these every time we use a power series approach to solve a differential equation. So, having already gone through that, let's get right to our ODE. We're going to save the initial conditions for at the end once we get the recurrence relation. But for right now, let's go right to our differential equation, and we're basically going to plug in the different power series representations that we have. Notice in front of the second derivative, y double prime, there's a coefficient of 1, which is nice. But in front of y, we have an x squared. Now, one of the other reasons you want to work with power series, besides them differentiating very nicely, is when you multiply powers of x, you can add their exponents. So if you take a look at your function power series for y, we're going to have basically x squared. That's this right here, and it's going to multiply x to the n. And just to save us a little bit of work, we can bring that x squared inside the summation, and we can write that as x to the n plus 2. All right, with that out of the way, let's go ahead and use both our power series representations for y double prime and then y, but the x squared bumps the power up from x to the n to x to the n plus 2. I'm going to take my time with this. I definitely recommend that to all my students. Write everything out in detail. It pays off in the end. So let's write our power series for y double prime. We have it as a sum from n equals 2 to infinity. We have n times n minus 1, c sub n, and then x to the n minus 2. We have the minus between. And we already, again, brought the x squared into the summation to give us now in our power series for y, x to the n plus 2. So we have our other power series. This one starts with n equals 0, goes to infinity. We have c sub n, and now x to the n plus 2. All right, now from here, what we try to do to get the recurrence relation is combine these two power series together, but there's an immediate problem. It's okay that your starting indices are different. Ultimately, we want to combine the powers of x together, but this has x to the n plus 2, and that has x to the n minus 2. We're going to need like terms. This is where we can use the technique or trick of shifting indices. Now we have two options. We could either shift everything to x to the n plus 2, or we could shift everything to have powers of x, x to the n minus 2. Now make sure when you shift that you don't end up with any negative indices. So if we were to try here to shift to, let's say, x to the n plus 2, I would have to replace here my n's with n plus 4. And notice if you do that here, n being replaced with n plus 4, you get n plus 4 equals 2. That would then solve to give you n starting with negative 2. So let's not shift to x to the n plus 2. Let's shift to the other term. We're going to shift everything to give us powers of x, x to the n minus 2. So we're going to leave this power series alone, and we're going to shift this term to x to the n minus 2. Now we can do that by replacing all n's here with n minus 4. And notice if you were to do that, replace that n up there with n minus 4. N minus 4 plus 2, minus 4 plus 2 does give you minus 2. All right, so just to be clear, again, we are taking our time. We're leaving this power series alone and only shifting this one. So let's just copy that one down again. So sum still goes from n equals 2 up to infinity. And now we're shifting everything from the video in the link below, the outline of where those 3 power series come from, as well as our tips and tricks. Make sure you're comfortable that when you choose this replacement, it's going to shift your starting index here. And make sure you replace all n's in the exponent, the subscript of your coefficient, as well as the summation. All n's get replaced here with n minus 4. Now, if we do that here, in that summation, the starting index, what we get, just to put this off to the side, is we get n minus 4, that's the left side, equals 0. And if you solve that simple equation, that shift now has our starting index for this infinite series starting with n equals 4. All right, so with that out of the way, we now have our summation from n equals 4 to infinity. Make sure you shift the subscript. That becomes now c sub n minus 4. And then shift your exponent here, replace n with n minus 4, and you'll get n minus 2. So we get our power x to the n minus 2. And don't forget to carry your right-hand side down, that's all equal to 0. All right, from here, we now have the same power of x, but the problem preventing us from combining these 2 power series together and then adding the coefficients is our starting indices are different. So that's not a problem. From here, once you shift your powers of x, we can just write out terms. And notice we have n equals 2. We can write out 2 terms, n equals 2 and n equals 3, and then our sum will go from n equals 4 to infinity. All right, we're going to take this, write out 2 terms. We're going to write out the n equals 2 term, and then the n equals 3 term. And then what comes after n equals 3? N equals 4. And then we'll be able to combine those 2 power series together. So again, take your time, replace all n's here first with 2. So we're going to get 2 times 1. That's going to be c sub 2. And then notice here we get x to the, that's going to be 2 minus 2, x to the 0. So we just get 2 times c2. All right, we now go to n equals 3. We're going to get 3 times 2 times c sub 3, and now we have x, or x to the 1. And then we have n equals 4 and all the terms beyond. And again, take your time and write all this out. All of this came from the first power series. We're just going to carry this one down. So we now have minus the sum from n equals 4 to infinity of c sub n minus 4 times x to the n minus 2. And we are basically done. We now have the same starting indices in our infinite series, our power series, and we have the same power of x. So we're going to be able to add these 2 power series and also add, or technically in this case, subtract their coefficients. Now we do have 2 terms in front. We have a constant and then an x term, but that's not going to affect our recurrence relation. We'll get to that in a moment, but let's write down what we have here. I'm just going to carry those terms. 2 c2 plus 6 C3x. And now we're going to combine these together into a single power series. The sum is now n equals 4 to infinity. And we're going to subtract or add those coefficients. So we get n times n minus 1 times c sub n. And we subtract this coefficient, so minus c sub n minus 4. Those were the coefficients of your like term, x to the n minus 2. And from here, we are basically done. None of the calculations here, I think, are difficult. We're really just adding and subtracting indices, writing out terms. But these are certainly very tedious, and they take a lot of time just to make sure you keep writing everything correctly. Very easy to lose track of a subscript, an exponent, or an index value. All right, now, how do we actually extract any information from here? How do we extract our recurrence relation? Basically, what we do from here is we're going to recognize on this left side, we have a constant, we have x to the first power, and then notice in this infinite series, this power series, with n equals 4, your starting term, 4 minus 2, that gives you x squared. This contains x squared and all higher powers. Now, this is not technically mathematically correct, but we've done this before. Think of this left side as an infinite polynomial. You have constants, x, x squared, x cubed, x to the fourth, so on and so on. And on this right side, we have 0. How we actually get the recurrence relation is we're just going to recognize all your powers of x on this right side. They all have a coefficient of 0. Now, you don't need to do this, but I like to do that in my courses. Write out all the missing coefficients or powers of x with a coefficient of 0. So 0x, 0x squared, 0x cubed, so on and so on. All right, so we're going to get a few conditions here in order for this to be true. The first condition we have is that this constant term, 2c2, we're basically equating coefficients on each side. This constant term has to equal that constant, so we get 2c2 equals 0. All right, now that tells us that the value for c2 is 0, which is nice. We get one coefficient value for free. All right, we have another condition here that comes from the terms that we wrote out. This coefficient of x, 6c sub 3, that should equal the coefficient of x on the right side, which is again 0. All right, notice that tells you c sub 3 is also 0. And since all the coefficients of the higher powers of x, basically from here on, x squared and beyond all have coefficients of 0, we now conclude that this term or expression in the brackets, that set of coefficients, has to equal 0 for all values of n equal to 4 and beyond. So our third condition is that n times n minus 1 times c sub n minus c sub n minus 4, that has to equal 0, and that is basically our recurrence relation. And that's most of the work for this question. Now, the second part of this video, which we'll be getting to in a moment, is how we actually use that with the initial conditions to get values for the coefficients, like actual numerical values, is we want to put that in a more useful form. And typically what we're going to do is solve this for the higher indexed coefficient. Now, if you just think for a second here, you might have several coefficients, but let's just take a look at how we might count. And let's say I have an integer n minus 4, that comes before. So our higher index term here is actually c sub n in terms of how we count with our indices here. So let's solve this for c sub n. Make sure you realize you, in general, want to solve for the higher indexed coefficient. And for this one, that happens to be c sub n. Depending on how you shifted and your subscripts and your indices, you might be solving for a different higher index term than c sub n. So this is very simple. We can just add c sub n minus 4 to the right side and then divide by n times n minus 1. So we get it here, c sub n as c sub n minus 4 divided by n times n minus 1. And that is your recurrence relation. That's what we try to work towards for almost every single differential equation that we solve with a power series solution approach. Now, this is only going to be valid for certain values for n, the indices, and usually you can check it just from your expression here, keeping in mind you don't want negative indices, and you certainly don't want to divide by 0. So notice this doesn't apply or work when n is 0 or n equals 1. That's going to give division by 0. We also want to make sure that we don't have any negative indices. So if n starts with 2 or 3, you do get negative indices. Now go back to your sum as a consistency check. Our sum here starts with n equals 4. And notice when n is equal to 4, we get a subscript or index of 0. So this recurrence relation looks like it's going to be valid for all values of n, the indices, greater than or equal to 4. So that is our recurrence relation. Which is what we are after when we solve a differential equation with a power series. All right, now that we have that, let's go ahead and address how we use the initial conditions to give us some starting coefficient values, and then how we iterate this to get as many coefficients as we want. Now that we found our recurrence relation, one of several conditions that we found, we're ready to find the values for as many coefficients as we want. Now make sure you realize the recurrence relation is one of 3 conditions that we found for the coefficients. The first 2 conditions were really simple. 2c2 equals 0 and 6c3 equals 0. We found those by writing out the first 2 terms in certain power series from before, and we can immediately conclude from those 2 simple conditions that c2 as well as c3 are both 0. So let's put that in our list. And typically when you solve an ODE with a power series approach, you might get conditions like that that give you 1 or 2 values for coefficients for free. All right, now I find for my students there's difficulties in one of 2 spots. The first difficulty they encounter is all the tedious work to get the recurrence relation. Now, once they get through that, there's another difficult part, but it's really not difficult. Students are just not used to making use here of the initial conditions in a power series. And I'm going to argue that it's actually really simple once you realize how to use your initial conditions. Now, notice here, from those simple conditions, we get the values of C2 and C3. What about the values of C0 and C1? Those are going to come from the initial conditions. So let's go ahead and use our initial conditions exactly like we would have before. We're going to plug x equals 0 into our function, and then x equals 0 into the derivative. Now, working with power series, this is really nice because notice, if this is our function y, plug in x as 0, almost all of your terms, those involving a power of x, evaluate to 0. If you plug in x as 0, you're just going to be left with c sub 0 on that right side. So let's go ahead and plug in our initial condition, which is y of 0 equals 1. So in other words, our y or function value is 1. And when you plug in x as 0, everything but c sub 0, in other words, your x term and beyond, they all evaluate to 0. We're left with just c sub 0 on the right side. And that immediately tells us c sub 0 is 1. So we can put that in our list. And we're going to do the same thing with our derivative initial condition, but now we're going to plug that into the power series for y prime, the derivative. All right, so our initial condition here is the derivative y prime of 0 equals a half. So our derivative value on the left is a half. And it's pretty much the same thing as how we found the value for c sub 0. We're now going to plug in x as 0 to this. Your x term and all higher power of x's evaluate to 0, leaving you with c sub 1. And that immediately tells us the value for c sub 1, which is a half. So we'll put that in our list. And this is a good time to probably mention something that happens in general. It's not a coincidence that c sub 0 equals your function initial condition and c sub 1 equals your derivative initial condition. That's true in general, that c sub 0 equals y of 0, your function value at 0, and c sub 1, that equals your derivative at 0. A short explanation for why that's true in general, our power series that we're using here, these are technically Maclaurin series. And recall how you find values for the coefficients of a Maclaurin series. Plug 0 for x, your center point, into the function and its derivatives. So not a coincidence thinking from the point of view of Maclaurin series, which is a special type of power series. All right, so far we have the value for C0, C1, C2, and C3. We now want to get as many coefficients beyond as we want. All right, this is where we're going to go to the recurrence relation, and we're going to start to iterate that. And we're going to find a pattern here. The fact that C2 and C3 are both 0, when we start iterating this recurrence relation, we're going to find that pattern of two coefficients equaling 0. That's going to propagate forward to higher indexed terms. So let's go through our list and now find the value for c sub 4. So we're going to basically plug everything into our recurrence relation. So I'm going to start with n equals 4. And I'm going to plug that in everywhere that I see in n. So c sub 4, we get now in that numerator c sub 0. And then we have 4 times 3. And this is where the aspect of recursion comes in. To get the value of c sub 4, notice we need the value of the previous term or coefficient, c sub 0, which we have. We have c sub 0 as 1, so if you plug that in, we get C sub 4 as 1 over 12. So let's put that in our list. Now we go on to C sub 5. Use your recurrence relation now where n is 5. So we get C sub 5. Now replace n as 5 everywhere, so we'll get C sub now 1. And divided by 5 times 4. And again, the aspect of recursion kicks in. C sub 5 is determined in terms of C sub 1, which we have as a half. I'm just going to be careful because I always screw up fractions in class. Looks like we can simplify that as 1 over 40. And we'll put that in our list. And now something interesting is going to happen with our previous values here for C6 and C7. So let's go ahead and just plug those indices directly into the recurrence relation. So next up, we would plug in n equals 6, and we get C sub 6. And now when you plug that in here, you get C sub 2 divided by 6 times 5. We know the value for C sub 2 as 0. Plug that in. That now gives C sub 6 as 0. So we can put that in our list. And you can probably guess what's going to happen for C sub 7 without iterating your recurrence relation. We're going to find a pattern. Anytime there's a 0 coefficient, it's followed by another one. Let's just check. So if we plug n equals 7 into the recurrence relation, we get C sub 7. Now we get, what's our subscript there? 7 minus 4, that's going to be C sub 3. Divided by 7 times 6. But C sub 3 is 0. So as expected, we get C sub 7 as 0. All right. Now you can probably anticipate the pattern here of coefficients. We get 2 non-zero coefficients followed by 2 zero coefficients, and so on and so on. So we might expect C8 and C9 to both now be non-zero. So we're just going to continue iterating our recurrence relation. Let's go to now n equals 8. And we'll plug that into our recurrence relation, so we get C sub 8. And just be careful with your subscripts. We're going to get a subscript there, 8 minus 4, so C sub 4. And now divided by 8 times 7. Again, I'm going to take my time here because I do not want to screw up the basic math in differential equations, but I inevitably always do anyway in class. But let's take our time. What's C4? We have that as 1 over 12. And if you go ahead and simplify that, divide, rewrite this, you should get 1 over 672. All right, so we can put that in our list. C sub 8, 1 over 672. And let's go to one last coefficient value, C sub 9. And again, just be careful with your subscripts. We now have, for our subscript, 9 minus 4, so C sub 5. And then in your denominator, we're going to have 9 times 8. All right, and again, we know the value for C sub 5, 1 over 40. And that's divided by 9 times 8. Work that out, and you should get 1 divided by 2,880. And we'll put that in our list, and that is the last coefficient that we're going to find. And again, we can recognize the pattern here. We get 2 non-zero coefficients followed by 2 zero coefficients. So what you should find, C sub 10 and C sub 11, those are both going to come out to 0. And then we can continue that and get as many coefficients as we want for our solution for y as a power series. And that's how we make use of the initial conditions and the recurrence relation to get the values for as many coefficients as we want. Usually for science and engineering purposes, when you use a power series to approximate a solution, science and engineering students, they usually just stop at the x term, neglecting x squared and beyond. But for differential equations, a mathematics course, we can get as many coefficients as we want. All right, I hope you enjoyed the video. Again, take your time with these like I did. It will pay off. If you're learning a lot, support the channel, like and subscribe.